Then we are going to study power series. Okay, power series, by definition, is going to be the series involving the variable x. Okay, so that means when x changes, you get different values, and you actually define a function. And we know that a polynomial is a function, right? A special function. And the generalized polynomial is called a series, power series. And we can use the power series to define a function. Actually, we can describe most of the functions. So let's begin with the following series. Okay, it's going to be, yeah, consider a series in the form, it can be start from any capital N, okay, and x minus a to the n. Okay, so this is called a power series. Okay. First thing we have to do is, for what the value x, it is convergent. Okay, since there are terms containing power functions, so we can use a ratio test or load test to check the convergence. But then the convergence depends on the value of x, of course. Okay, so let's try to use ratio test. Okay, this is our an, right? So you take a look at the limit of this, if it exists. So we find out, here's cn plus 1, here's x minus a to the n plus 1, here's cn, right? So let's simplify. I cannot simplify this ratio. We don't know the cn here, but I can get x minus a here, right? Now I have to make an assumption, okay? Because if it's too bad, the coefficients, I cannot determine convergence. So I have to assume that this limit exists. Okay, this limit exists. It could be positive infinite, could be a non-zero finite number. Okay, yeah, because it's non-negative number, right? It's a limit can be or finite a number. Okay, and or zero, non-zero, positive finite number. Okay, I should say positive finite. Positive finite. Yeah, put this way. I just simply write a number a, okay? A positive. We assume this is this exists. Then you end up with this limit, right? N approaches infinity, right? And so there's a limit here. N times x minus a. So the question is, for what x, this is going to be less than 1. If it's less than 1, it's convergent. Otherwise, it's divergent. Okay. So I'm going to denote this part by 1 over r. Okay. Here, what is r? 1 over r is going to be the limit, right? So it depends on the value. Okay. If the limit Yeah, if R could be 0, could be 1 over A, could be infinity. Okay, it depends on the limit of the Cn over Cn plus 1 over Cn. Okay, so this is the rate this is the number we need. Why we have put it in the denominator? Because I want to make sure this is greater less than 1 or greater than 1, right? So clearly by the ratio test, if x minus a is less than r, then this series is absolutely convergent. Okay, then this is the absolute convergent. Okay, we also know that if x minus a greater than r, then it is divergent. It is interesting. Why? Because look at that, right? X minus a less than r means x minus a divided by r less than 1. Okay. So let me put a note here. X minus a less than 1 equivalent to saying that x minus a is less than r. Okay. Right. All right. So there's a very strange number here, special number. So you can determine an interval, okay, around the a for x in the interval, the series is absolutely convergent. For x outside interval, the series is divergent. So we just don't know what happens at the end point. That's okay at the two end points. But that's an assumption the limit exists. Okay, the limit exists. This limit. Okay, this limit exists. Otherwise, we cannot get this conclusion. And similarly, you can use the root test. Okay, if you look at root test, you will get the limit nth root, right? When you look at the nth root, so this is going to be nth root of absolute Cn times x minus a. So you just need to worry about this part. Okay, by the same assumption, we have to assume that this nth root equals 1 over r exists. Exists means either infinite or finite. Okay, so exist means either infinite or finite. Yeah, it could be positive infinite or a or 0. In the three cases, it's positive. Okay, some no. Then you can use the same idea, you can use a ratio root test to conclude that if x minus a is less than r, then the series is absolutely convergent, right? Otherwise, it's divergent. So I guess you can use any of the tests to get this conclusion as long as the limit exists. Okay, so this is a divergent. Okay, divergent. Okay, now let's take a look at examples. This is a good example. We are given the series just xn. So xn, x to the power n means x to the x minus 0 to the right, and the coefficient in front of that is just c, just 1, right? So this is the power series, right? So we want to determine for what x it is convergent. So you can use any test, ratio test, row test, doesn't matter. So let's use a ratio test. Okay. For the ratio test, you needed to look at this, right? Okay. So we repeat the above procedure to determine the values x for which the series is convergent and all that. So it's going to be absolute value x plus 1, right? So after simplifying this absolute x, so it's constant. The ratio is constant. It is not going to be right. It's easy. Of course, it's convergent to x. You just apply, and in this case, I is 1. Okay, honestly, I equals 1. I equals 1. Okay, if you see, because Cn is always equal 1, so the so that is 1. So that approach it's 1, right? Approach is 1 of r, so r is going to be 1. All right. So we conclude that if absolute x is less than 1, then this series it starts from 1, right? Doesn't matter from 1. Xn is absolute convergent. Okay. Now, second, yeah, you forget the radius, okay? Forget the r, forget r, but just use applying the ratio test to this problem. What you can see, if x is greater than 1, absolute, then the series is divergent. We cannot say anything about when x equals plus minus 1, but you can look at when you look at x equals 1. Look at the case when x equals 1. So when x equals 1, clearly, yeah, case by case, right? Clearly, this is a divergent. Okay. How about x equals negative? It is also divergent. Okay. It is divergent just because the nth term. That's not equal to 0. Okay. So we completely understand this series. This series is convergent for x in the open interval from negative to positive. If we draw the line, okay, if yeah, so I can let f of x to be sigma, right? But this is only defined for x less than, for x is absolute value x less than 1. Okay, so what? Yeah, this only holds because the right hand side is only defined for absolute x less than 1. Okay, so for x, otherwise, like the right hand side is divergent, it has no value. Okay. So I left this, right? So you get a new function. The function depends on x. We just proved that for x between negative and positive 1, this series is always convergent, absolute convergent, and then convergent to some number that depends on x. If it's dependent on x, you get a function, right? So we use a power series. We get a function. This function may be nice, maybe elementary function, but this is polynomial, right? Generalized polynomial. The degree is infinity, but it's only defined for x between negative and positive. Okay. Now, it is possible this series actually convergent to a nice function, okay? Using elementary, convergent to an elementary function, which is defined in the by the simple formula. Let's see. We know that for x less than 1, right? Sigma n start from 1 to the xn, right? It's going to be x to the 1, x squared, x to the m, right? So we can add them together. You can take x out, okay? And then remember, this is geometric series, finite geometric series. So this is going to be 1 minus x to the n, m. Okay. So if m approaches infinity, this clearly approaches x 1 minus 0, 1 minus x. If m, yeah, as m approaches infinity. Right. So what does that mean? That means this power series is going to be x over 1 minus x, and this power series is converging when x less than 1. All right, this is identity. It's holds for x up to x less than 1. But if you look at the function, the formula on the right-hand side, this is defined for much larger, value, right? So x can be beyond that interval. Okay. So we note that this part, this can be defined for x outside the interval. Okay. So this is this function itself. We look at this. This is defined for x not equal to 1. That's it. Right? This is defined for x not equal to 1. X could be less. X could be negative 1 and negative 10. Okay. How can I say? Okay. So we look at functions. Okay. And here's one. Okay. This is the vertical. If you draw the line, it goes like this. X when x is getting close to 1 from positive side, x is positive, I think it goes like that. Okay. When x goes to positive infinity, hold on. So this is a negative side. Okay. So for x greater than 1, for x greater than 1, denominator is negative, numerator is positive. It goes like, okay. This is horizontal line, y equals negative. And the other one would be like this. This is a graph. This is a graph for y equals x1 minus x. Now, what we did here is for x between negative and positive, for x here, for this function, I can approximate, express by a power series, only for that piece, not for the general. Okay? So when I'm saying that, this function over the interval from negative to positive, okay, matches with this power series. All right? It's interesting. And when x equals negative 1, this power series is divergent. Okay, but the function on the right hand side is defined. Okay, so that matches only when x is between negative and positive. Okay. Now you may wondering, can I describe this piece okay, as a power series. It's possible. Okay, you take an arbitrary point which is not equal to A. Okay, let's say you take an arbitrary point A, which is not going to be 1. Either on the right hand side, left hand side. Okay, I can draw the interval around that. This is R. Okay, I can find a power series converging to the function x over 1 minus x. Okay, how can I do that? Okay, and the radius is going to be, from the picture, is A. If A is positive, greater than 1 is A minus 1. If A is negative, it's 1 minus x. So let's just put up a through it. Okay, A minus 1. Okay. As long as A is not going to be 0. As long as A is not going to be 1, then I is positive. Okay, yeah. So I is positive now. So I'm going to find the power series representation for this series when x minus s less than r. Okay. So all I have to do is determine the coefficient. Right? It's not trivial. So this is a the standard technique. We're going to do that. Okay. How can I do it? I express x as x minus a plus a. That's the trick. Okay. So for the simplicity, I just simply write the u plus a. Okay, u is going to be x minus a. Okay. I'm going to rewrite this function. Okay, it's going to be 1 minus u plus a. Okay, yes, u plus a. Okay, I'm trying to find a good formula. Okay. So what I'm going to get is 1 minus a minus u plus a. Okay. Well, it's not good, right? So what I'm going to do is I'm going to take 1 minus a out. So I get 1 minus u over 1 minus a. And here's u plus a. Okay. So we have to have two functions separate. What I'm going to do is I'm going to use the following formula. Okay, I'm going to use the following. So if we start from 0, and the w to the nth power is going to be 1 over 1 minus w. Okay, as long as w is less than 1. Now if you start from 1, we already see that there's w on the top. Okay, this is what we're going to use. So pretty close, right? So I continue to express that function. Okay, I'm put u have a 1 minus u minus 1 already, and I'm going to. Okay. All right. Let's continue. I think I needed to divide this by 1 minus a, and you multiply the 1 minus a here. And this is constant here. So what I get here is u over 1 minus a. And here I take a constant out. Okay. So using the above formula, W here is going to be U1 minus A. Okay, so the first one gives you, if give you this, n start from 1. Okay, the second one starts from 0. Okay. You can ignore the first term. So the first one, when n equals 0, just 1. So A over 1 minus A. Then I can combine those two terms, right? So it's going to be 1 plus A over 1 minus A. And this is U minus A to the nth power. Okay, let me repeat again. So this added them together, just 1 over 1 minus A. So I can simply write one, and I have another one from the other side, it's U to the N. Okay, so this is what we get. Okay, since U is X minus A, so I can just simply replace it by X minus A. So this is a power series. It is convergent when absolute of U is less than 1. Okay, it is convergent when absolute value of U minus 1 minus A is less than 1. Now, if you rewrite it again, it's in this form. This is what denoted by R, right? We know. Okay, IE is X minus A is less than R. Okay, for X minus less absolute value less than R, then you get power series. Let me summarize that. Okay, so you can, okay, you can express this function as power series. Oops. As power series for X close to A. Okay. So this can be expressed as power. Okay. It's too bad. Try not to touch the screen. All right, so yeah, anyway, this is a convergent to just the bubble, right? So that's, you don't copy. All right, such simple function. No matter where you choose a number A, as long as A is not going to be 1, then around that number A, you can always express the power function as you can express that function X over 1 minus X as a power series. Okay. But in many cases, the power series you're going to get, even you know the interval on which it's converted. Okay, you only know it's defined some function, but you cannot express that function using elementary function. Okay, that's twofold. One is almost all the well-known elementary functions can be expressed as a power function at any point where it's defined. Okay, a small neighborhood. You can always express it as power function. That's what I did, like this one, x over 1 minus x. This function, what is it to make? To make this is a whole line except for 1. Okay, then you pick an arbitrary point, which is not equal to 1. Then nearby that point, I can express this function as power series. Okay, and that power series is not going to be convergent everywhere. It's only convergent in this interval, and I is going to be 1 minus absolute. That means it cannot pass the number 1. Okay, so if you look at the picture, this is a 1, right? This is the 8. So this R is absolute value 1 minus 8. That cannot be larger than that, because otherwise this interval will containing 1. Okay. Okay. So from picture, we already know what is that, but we can wrap that formula. But on the other hand, we have so many power series which are convergent to some function. Those functions cannot be expressed by any elementary function. Elementary functions means the function is already familiar with sine, cosine, exponential. Okay, so that means the class of elementary functions. Okay, just think about the milk. Okay, and the class of all the functions defined by power functions. It's like a universe. Okay, so there are almost all the functions in the world cannot be expressed as elementary functions. Okay, can be expressed. So in engineering, if you have to deal with some equations, we call different equations. Yeah, according to some physical law, this quantity, that quantity, that derivative, the rates are satisfied. They satisfy some identity equation. And that's called differential equations. And trying to solve it, you cannot solve it in the sense you cannot express a solution as an elementary function. But the solution exists. Okay, it defines some function, solution function. But you can use power series to describe the solution. And that is our motivation to study power series. The power series defines almost all the good functions, nice functions. But that is very huge and large class than the class of elementary functions. Right? And the more you study mathematics, you find that you understand less. Okay? It's the same, you more you learn about the universe, you find that you understand less, right? We try to go to Mars and to find out that we almost know a little bit about the universe. Okay, more technology you introduce, we find out that we understand much less. So yeah, as a first grade, the student I can do all the division multiplication. I know everything. That's true. Some kids I'm great. I'm best student. I know everything. All the math problems. Actually, he only just know the division multiplication. Okay. So now this is we are going to see lots of functions which cannot be described as elementary functions like x over 1 minus x. Let's take a look at the example. Okay, this is a problem. Problem number 4, I guess. It's n starts from 1. Okay, so it's a kind of alternating series, but it's not exact. Why? Because x could be negative, positive. Okay, but this is a function. You define function. I'm going to define the function, and then you have infinite terms there. Number one is you have to know on which interval this series converges. Then you define the function on that interval, right? Because if it's convergent for any x in that interval, then you get a value every time as a limit. And that limit depends on x. Then you get a function. Okay? So I want to know a couple things. One is on which interval it is convergent. Okay? That's all you needed to know. Okay? And later on, we're going to do some computation like the derivatives or integrals of this function. We can do that. Just treat it like a polynomial. Okay? But this is an infinite many terms, a polynomial. We know we can freely do the computation. What is the derivative of polynomial? You just differentiate every term, right? So let's look at this. What I'm going to do is I'm not going to look at Cn, actually just An, okay, because we're going to repeatedly using the ratio test or row test. I'm going to use the ratio test, okay? I want to see, when the series convergent or divergent. All right, so take a look at this. The negative sign is already gone. So absolute of x plus 1 here. 3 as the third root of plus 1. All right, so now after simplifying, put x together, okay? And you put the third root of those two terms. All right, so now you simplify a little bit, okay? You want to define the limit. So absolute x is here, and this is a third root of n over n plus 1, right? The third root of n over n plus 1 always convergent to 1, because n over n plus 1 converges to 1. So my limit is just x. Very simple. So according to the ratio test, okay, what you can see, if this is if x is absolute x is less than 1, then this series is convergent. Not only convergent, it's absolutely convergent. Okay. Right. And when if x is greater than 1, it is divergent. It means the series. So now at least I know there's open interval from negative to positive. So what x in the interval, it is absolutely. How about the boundary, the end point of the interval? So we needed to pay attention to that. So the third one, case by case, when x equals 1, okay, the series becomes the third root of n, negative 1 to the n. I think it's convergent. It's obvious. It's convergent. It's not absolute convergent. Okay? It's absolute convergent. Okay. But its condition is not convergent. If we remove the negative sign, it is divergent. Why? Because it's n to the 1/3. 1/3 is less than 1 by the P-series test. It's divergent. So you just needed to say it is convergent here by the alternating series test. You can skip some argument if the problem is too long, but you have to say that by which test. Okay? I know when you say that guy, I know you know how to solve the problem. Cannot just say convergent. Then it's just my guess. Okay? We don't know it. So when x equals -1, what do you get? When x equals -1, you will get the series, the third root of n, it's just 1. And -1 to the power n, -1 to the power. And this is a divergent by the P-series test. Okay, so now it's clear that this series is convergent on some interval. So now your conclusion is this series is convergent on the interval from -1 to +1 closed. And inside the open interval is absolute convergent. At this endpoint, it is conditional convergent. So the convergence is not that strong. And very often at the endpoint it's divergent. Sometimes it's convergent, and usually it's a conditional convergent. Okay? Very few cases get absolute convergence. So anyway, you get it's convergence, and we get a function. Okay, and on that interval. Right? Can we express this function using elementary functions? I don't know. Okay, and I don't think so. Sometimes you can, sometimes. If this is a function you get from very special equation, and that equation becomes very popular, like Maxwell equation, okay, then spend time trying to study, understand this function, how this function behavior, when x approaches to 1 from left hand side, and something that you draw the graph, you write a paper, you put a picture there, and if really turns out to be very important function, nobody use it, discuss it, then they will give you credit about that. Okay? But they will, be named after you. But the problem is that they are very limited, the last name here. So that's called a Taylor series. You know how many Taylors right? If you look at Yellow Book, so many people with the last name Taylor. All right, so this is a function. It's hard to see how does it look like, right? But I'm pretty sure this function has a value 0 when x equals 0. If you draw the graph, if you draw the graph, the graph passes through the origin, okay? Okay, let's look at other problems. And here's another one. So n power to the xn. Try to determine x for which it is convergent. So I use an nth row test, okay, not a ratio test. Ratio test doesn't work. So nth row, this is my n. Okay, it's going to be okay, and actually it's n times x. So what is the limit? This limit is going to be the only two possibilities. And it goes to either power infinity if x is not going to be 0, or 0 if x is always 0, right? So only when x equals 0 it's convergent. X is not equal to 0, the limit is infinity, so it's greater than 1, therefore it's divergent. Okay, so my conclusion that it is convergent if and only x equals 0. Alright, so the radius of convergence is 0. So this function, this power series, you try to use it to define a function, but that function is not defined on any open interval. It's only defined at one particular point, 0, which is going to be 0. Okay, so that's it. So this is not a good function. Okay, so you cannot define a good function here. Okay, so let's try next one. Right. Right, again. Ratio test, row test doesn't matter. Okay, let's use a nth row test. Yeah, the row test. Okay, so it's going to be because there's no n factor there. That's the reason I can use the row test. When I can use ratio test, I usually can use row test. So simplify that, you will get just absolute xn and right there. So you can also write like this. So the answer will be, after simplifying, this. So clearly the limit is itself. Right? This is already the limit. It's independent n. So we know that if absolute x squared is less than 1, the series is convergent. Okay? It is absolutely convergent. Right? And if absolute x is greater than 1, it is divergent. And I think in this particular case, when absolute x over 5 is plus minus 1, it's going to 1, this is divergent. Okay? So if absolute x is going to be 1, so that means, yeah, then you look at this, right? Look at the nth term, right? The nth term, let me record that. Let me go back. Yeah, it's going to be this, right? So this absolute term is nth term is nothing but equal to 1. Why? Because negative sign is gone. Absolute x over 5, right? Now you can get something like that, which is 1. Okay. So that means it does not approach 0. Right? This implies n does not approach 0. I don't care whether it has a limit, but does not approach 0. So this implies the series is divergent. In this case, right? It is divergent. Now, so we get a function, right? We get a function. Which is defined by this. Good. So we get a function on the interval. I think absolute x is less than or equal to 5, from negative 5 to positive 5. Right. because this series is convergent to an absolute value of x less than 1, right? Divided by 5 less than 1. So the interval between values being coordinate of -5 to +5. Oh, it's a nice function, right? I like it, you know. But in this case, this function defined in Power series is not a string function. It is actually come from elementary function. Okay, the function we are familiar with. Okay, how can I do that? I'm going to show. Okay, I'm going to rewrite this. So this is going to be -1 times -1 to the n x to the 5n, right? So I take a negative sign out, and I put -x to the 5 to the n. Then this is a geometric series. Okay, so that is going to be negative x over 5, 1 minus negative x. The formula I'm using here is sigma w to the n is w over 1 minus w is absolute w is less than 1. Yeah, this here ends up on 1. Right, so we simplify this, we get x over 5, 1 plus x over 5. And then I continue to simplify it to x, get 5 plus x. So that's a bit simple function, right? We got this, we got this function, pretty nice. So sometimes the power series you define it's not a strange function. It's actually it can be defined by elementary function. I just say most of the cases, randomly write down a power series, and if you show this is convergent to some function of a unit, that function does not belong to the class of the element function. Okay. So mathematicians still want to find a way to understand those power functions defined by power series. So then we try to, what I should say is that we try to find some simple like an estimate, or if you know the coefficient, how can you tell the behavior of the function, something like that. So there are lots of papers on this subject. Okay, I'll stop here. My next class will continue on the power series.